let's talk about energy. What is it? And how does it work? How is it measured? And what does it all mean? I'll be discussing this in the next few clips over some poorly drawn whiteboard noodles. There are 4 major ways to describe energy: watts, amps, then we have resistance, and finally we have volts. Each does something unique, and they all influence each other in some way. There are many ways to visualize just how energy works, how volts interacts with resistance, and how amps interacts with wattage. But the easiest way to visualize it is using a water in a hose analogy. Here, the water that I'm drawing in the tank represents the volts. It is also water pressure. Amps is represented by just how much water is actually flowing through the hose. The nozzle there represents resistance, how much water is restricted from flowing out of the hose. And wattage, finally, is represented as a small pinwheel, and how much work the energy can actually produce. Another way of visualizing amps, volts, resistance, and wattage is using a dam analogy. Here, volts is represented by the amount of water that's backed up behind the dam. The more water there is, and the higher the water, the more volts. The piping through the dam is similar to amps, and how much water goes through it, and resistance. Smaller piping will represent higher resistance. The corkscrew there represents watts. The faster the turbine spins, in this case, the more watts the water can produce. Finally, we can all sum up it together by saying that watts equals volts multiplied by current. And current, of course, is amps in this case. The higher the volts and the higher the current, the more watts an electronic device will produce. Now, how does all of this influence real-world activities? In our case, computers are an integral part of daily life. In 1990, there were just 275 computers on campus. In 2000, that number boosted to 511. In 2005, that number grew still to 750. But here we are in 2014, and Stockton's campus has 821 total computers in all labs and all classrooms. That makes for a difference of 71 total computers. All of those computers commands a tremendous amount of energy. In 1990, the average computer, while running, consumed 230 watts. 140 watts was being used at idle when the computer was asleep. In 2000, those numbers fell 190 watts active and 100 watts during standby. In 2005, the number fell some more to 110 watts when active and 30 watts in standby. And in 2014, we have 48 watts for a computer fully active, down to 1 watt when it's asleep. How does that happen? One of the biggest advancements in the last couple of years was the use of something called timer coalescing. Now, what is timer coalescing and how does it work? It's really just a fancy way of saying computers now use less energy. We all know that computers have a CPU, and the CPU handles all of the tasks and applications that are running at any given moment. The more applications that are running, the more CPU energy is needed to keep it going. If we were to zoom in on part of a graph, we'll see that instead of having it being smooth and continuous, it's really sharp, jagged points and lines where the CPU has to spool up and down rapidly to keep up with demand. This spooling is a very, very inefficient process. And what timer coalescing does is it takes those spools, much like a car revving up and down at many red lights, and compresses them into small chunks of time, which keeps the processor idling longer, therefore using less energy. Televisions and vending machines. One of the problems with vending machines is that they must remain on 24 hours a day, 7 days a week. This is to keep their contents fresh and from spoiling. The same goes for televisions. On campus, the televisions are on continuously throughout the day, despite having no one on campus to view them.
The 2009 energy audit of outdoor lighting of Richard Stockton specified two main issues of inefficient lighting on campus. The first was overlapping or overlighting of certain areas, and the second was the use of non-directional light fixtures, which cast light inefficiently in all directions. Since 2009, the campus center and the United Science Center have been built, which has led to an increase in outdoor lighting. The majority of newly installed bulbs are metal halide bulbs, and while aesthetically favorable, metal halide bulbs last half as long as high-pressure sodium bulbs, use more energy, and contain more than double the amount of mercury in each bulb. The increase in outdoor lighting has also resulted in more cases of overlighting and greater inefficiencies. Although Stockton is continually looking to advance the efficiency of outdoor lighting, it only represents 2% of the total electricity usage, so large-scale retrofits are hard to justify. However, a study conducted at the FAA Tech Center demonstrated that high-cost, efficient LED fixtures could pay themselves off in 3 to 7 years and reduce outdoor energy usage by 50%.